So this is our physics lab 2, and in this lab we're going to look at motion of a falling object. Topics covered in this lab are Newton's second law, gravitational force, drag force, and we're going to take a brief look at terminal velocity. Important equations for this lab were the velocity and position update formula, in addition to the formulas to find the magnitude of the gravitational and drag force. So for my experimental setup, I dropped a Starbucks cup from rest, and I set up my axis so that the cup started at the origin and moved in the negative y direction, as you can see in that video. So for my computer model code without drag, changes that I made to the starter code included t being less than 0.45, and this was because this was the length of the tracker video. And I also had fnet assigned to a variable called w, and this variable w was equal to the gravitational force, which I found by multiplying negative g times the mass of the ball and then multiplying that by the j hat vector. So our final gravitational vector was 0, negative 9.8 times the mass, comma 0. And I used the velocity update formula and the position update formula to update the velocity and position with each iteration of our loop. For my computer model with drag, all of the changes from the previous slide were also made to this code. However, we had to make some additional changes to include the drag force. In this case, we had to find our proportional constant b for the drag force, and this was found by trying different values until the final velocity in the model matched the final position in the model matched the final position in tracker. Once we found b, we could find the drag force by multiplying b times the magnitude of the velocity squared and then multiplying that by j hat. So for our fnet, we had to include the drag force, so we added the gravitational force and the drag force. In this model, we also added some arrows to represent these forces. To do this, we had to multiply the gravitational force and the drag force by a constant, which we referred to as arrow scale, and this was used so that the length of the arrows would be proportional to the magnitude of the force. So if you take a look at the model and we run it, you'll be able to see that the large orange arrow is the gravitational force and the smaller blue arrow is the drag force. So when we put all these data points into a graph, we can make two key observations. These being, there's a difference in the final y position. Both the model with drag and the experiment ended at negative 0.41 meters, while the model without drag ended at negative 0.81 meters. And the curve shape is different with each of these models. The model without drag is steep, and the model with drag is a little bit flatter, and then the experimental curve is the flattest. So some conclusions that we can draw from these observations, for the difference in the final y position, this is explained by the fact that the model without drag is going to fall further because there's no opposing force to the gravitational force, while the model with drag and the experiment do not fall as far because their delta v is smaller, and their delta v is smaller because their fnet is smaller. The fnet is smaller because f drag is moving in the positive y direction and f grav is moving in the negative y direction. So these opposing forces will make your fnet smaller. And then the difference in the curve shape can be explained by the fact that the model with drag and the experiment are approaching a terminal velocity. Terminal velocity is when the velocity is constant of a falling object, because the force of the drag force and the gravitational force equal each other, so the fnet is 0. As you can see in the model with drag and the experiment, they flatten out, especially towards the end, because the line is approaching a constant slope, and a constant slope is indicative of a constant velocity. So the model without drag will be steeper